Hello and welcome to Lecture of Artificial Intelligence course. Our today topic is Hidden Markov Models, which is the basically dynamic or spatial extension of Bayesian networks, or it can be viewed like that. This lecture is quite long and it contains quite a lot of materials. We will most probably not finish it today, but we will finish the rest of the lecture next week. But we should cover at least those parts that are needed today for the lab exercises, which shouldn't be an issue probably. Okay, so let's move on to the actual meat of the lecture. Before we dive into hidden Markov models, we will first look at what Markov models are, and we will see then how they are extended with those hidden parts. So what are Markov models? This is partially a quiz for you, and well, this is a quiz for you, and it is partially a reiteration of what we have learned last week, not yesterday. So assume that we have a set of random variables from x1 to xn, and their joint probability distribution can be, without loss of generality, basically factorized as the product of these factors. And then you will learn that in our domain that we are trying to describe by our probabilistic model, it is quite reasonable to assume that each xi is independent of all those previous ones, x's of all those previous random variables, if you know the first predecessor. And now the question is, with this assumption in mind, how does this factorization at the top actually change? What is now the right factorization? So try to answer this question. A, B, C, D. Okay, the answers are coming. That's great. Let's wait a few more seconds. I have the majority of answers already. Okay, so thank you very much for your answers. And the majority of you is actually correct. B is the correct answer. Basically, this situation means that we have one variable like x1, another variable x2, then variable x3, variable x4, etc. And for example, this factorization, the top one, the general one, if you would like to describe the factor with x4 here, that would mean that you have to condition its distribution based on the values of all previous variables, right? But if you learn now this additional assumption can be applied, that x4 is basically independent of x1 and x2 if you know x3, This means that these two dependencies are basically thrown away. And if this holds for, excuse me, for all random variables, then it means that we have just a, let's say, linear sequence of dependencies, right? Each variable basically depends on one predecessor. And that's what the second option tells you, and that's the correct answer. So it seems that this independence assumptions thing is more or less clear to most of you. That's great. So let's move on. What I have just drawn was a particular structure of a Bayesian network. And last week we talked about Bayesian networks, mostly in the context where each variable in the model describes a different feature of the real world, right? There was a variable like pain in mouth, for example. There was a variable for cavity in your teeth. There was a variable for whether outside the weather is rainy or not. So these were all different aspects of the, let's say, current state of the world. But basically, we are not limited to this kind of description. We may basically define the individual random variables to be, for example, the same feature of the real world, but in different times, in different time instants, or the same feature on different places of the real world. Right? So very often we need to reason over the same state variable over time or over space. So we need to introduce these things into our models. And these Markov models and hidden Markov models are one way how you can actually approach it. This time or space dimension is basically very useful in many areas of artificial intelligence. For example, in speech recognition, there is some kind of hidden state of what vowel you try to pronounce, and the observation is basically the sound that you hear, right? The frequency that you detect at certain moment of time, and the succession of these frequencies gives you some kind of signal, and you can model this as a succession of values of random variables. So you can apply similar things in robot localization, in medical monitoring, language modeling, DNA analysis. So there are many application areas of these sequence models. So we will basically model the changing world actually as the state of certain state variables at each point of time. So we will basically split the running time or space into some slices, and we will describe the state using these slices. So random variables that will form sequences of in time or in space. And how we will denote these sequences. So you are already accustomed to this kind of notation, that X with the subscript of T means random variable number T. But here, the number T will basically denote most often the time. So it will be the state of the random variable at time 1, at time 2, at time 3, etc. These variables then form a sequence, and we will denote the sequence as this using this subscript and superscript, meaning the states of x at time a plus 1, a plus 2, a plus 3 up to time b, right? So this will be the set of variables from xa to xb. We will very often see this kind of thing, which will mean the whole sequence of variables x from 1 to t. So I think that this notation is quite clear, and we don't have to explain it more. Now let's move to the Markov models. This is the picture that you have seen already several times, where each variable depends basically on all its predecessors. Okay. So if you want to describe this model, you have to specify all of these conditional probabilities, basically. So you have to define what is the probability of xt given the values of all the previous values, the previous random variables. And as you can see, basically, and I hope that you all see this, that the conditional probability tables, which are used to represent these probability distributions, are basically getting bigger and bigger with increasing index t. Right here, you have only one parameter that you have to specify because there is no parent. Here you have two parameters that you have to specify because there is one parent, and it can have two values. So if all xi are from 0 to 1, sorry, not from 0 to 1, but from a set of two values, 0 and 1, then this variable would have four parameters, or the conditional probability table for this variable, because you depend on two binary variables. This gives you basically four different cases that must be handled. And you have 8 parameters here, etc. So this is basically not a structure that is somehow, generalizable to infinite sequences or something like that, right? So the first thing that we can do to simplify the things is to use the so-called Markov assumption, and that's the assumption that basically gave the name of the whole class of models. That's the Markov models, right? And the Markov assumption basically tells us that the current state depends only on a finite fixed number of previous states, such that this thing here cannot grow. The conditional part cannot grow. And if this is fulfilled, then we call that process a Markov process or Markov chain. So you can basically meet first order Markov processes, which are the most, you will meet them most often, because any higher order Markov process can be basically transformed into the first order Markov process, right? Because if a state variable depends not on one previous state, but on two previous states, then you can define two successive states to be one state. and you will basically transform it to the first order Markov process. So we will basically work with only the first order Markov processes here. And this gives this nice linear structure of the Bayesian network, basically, that describes the joint probability distribution. But even this simplification, the Markov assumption, is not enough, because if you would have to specify here like probability of x1 given x0 and probability of x2 given x1, sorry, x1, and probability of x3 given x2, etc. This would still mean that you have an infinite description of the model, right? So these factors are of the same size, that's true, but they can be different. Each can be different. And if you have to specify all of them for infinite sequence, you basically cannot describe an infinite sequence here. So there is the second assumption, which is the stationarity assumption, that tells you basically that for any xt and any different xt prime, these two probabilities are basically the same, right? So all of these transitions are basically described by a single model, probability of xt given xt minus 1. And thanks to these two assumptions, Markov assumption and the stationarity assumption, we have a class of tractable models, models that we can basically specify quite easily. We can reason about them quite easily, and they still have some practical values, meaning that you can apply them to modeling some practical tasks. Okay, so if we assume a stationary first order Markov chain that looks like this, then the Markov chain joint distribution can be basically factorized as this thing, right? So this is the joint distribution over the sequence of random variables from x0 to xt, and you can factorize it to this product of simpler probabilities. This factorization basically is possible due to the independence assumptions that we already talked about, that xt depends only on xt minus 1, and given xt minus 1, it's actually independent on all the previous predecessors. This can be informally stated as that the future x is conditionally independent of past x given the present x. This is, let's say, some mnemotechnic help that many people actually use to somehow memorize these assumptions. And it turns out that in many cases, these assumptions are actually reasonable. And because they simplify the things quite a lot, we can do the reasoning in polynomial time and space, which is a huge advantage over the general Bayesian networks that we talked about last week. And we said that the precise reasoning in Bayesian networks has actually exponential time and space complexity. And for big problems, we are not able to do that. In these things for hidden Markov models and Markov models, thanks to their simple structure, we are able to do that. In a way, you can think about the Markov models just as a growing Bayesian network with a very simple structure. And it would be true basically because everything that holds for Bayesian networks with those structures actually holds for the Markov models. This may be a simple example of Markov chain, and there will be a quiz related to this example. So let's assume that we have a Markov chain that somehow describes the behavior of the weather outside, right? So the variable x is the weather, and it can have two values. Maybe it can be rainy or it can be sunny outside. No more values possible, okay? And then we have something that we call transitional model, which is basically just this conditional probability. What is the probability of the current states given the previous state? And you can write it in the form of this conditional probability table, CPT, that tells you something like, yeah, if yesterday was sunny day, what is the probability that today will be sunny day as well? Well, it's 0.9. If yesterday was sunny, what is the probability that the weather will change to rainy? Well, it's 0.1, etc. The same thing, the same information as is encoded here in the conditional probability table can be, for example, described by this state transition diagram, where we describe basically the whole process as a kind of automaton. So you you specify here the possible values, and the transition probabilities are on the arrows. Or you can specify the same thing as the state trellis, as it is called like this. And you can, for example, see that for yesterday values, yesterday possible values of the weather, what is the probability of transition to the values of the weather for today. So all these three things are basically equivalent in that they hold the same information. Okay, and now the quiz for you. Given this particular Markov chain, or the transition model of the Markov chain, what is the weather distribution today? So we ask for the distribution over the two values rain and sun at time 1. If we are unsure about the weather yesterday, so we basically state that our belief in rainy weather yesterday is 0.5, and our belief about sunny weather yesterday is 0.5 as well. So what is the current belief for today? And you have again 4 options, A, B, C, D. So let me know what you think, which one is correct. So the answers are coming. Let's wait a few seconds. Okay, so it seems that everybody who wanted to answer already answered. So let's stop the survey. The majority of you thinks that option C is the correct answer. Indeed, it is. Thank you. Why is option C the correct answer? Well, because if the rain state had a probability of 0.5 yesterday, and the sun state had the same probability yesterday, then it actually means that with probability 0.5 times 0.7 plus 0.1 times 0.5, we get to this rainy state for today. And because of this uniform distribution, it is just an average of these 0.1 and 0.7, right, which is 0.4 for today. And using the same process, 0.5 times 0.3 plus 0.5 plus 0.9, you will basically get the probability of the sunny weather for today, which is 0.6, right? So 0.4, 0.6 is the correct answer. It seems that quite a lot of you got somehow confused. Maybe it was caused by this explanation here. If there is no info about yesterday, how can we say anything about today? And you may say, yeah, that's reasonable, right? But it's actually not generally applicable because there is this transition model and you know that it holds. And maybe it may look like this. So it will give 1 to sunny weather for today, no matter what was the state yesterday. So even if you have no information about yesterday, this conditional probability table here gives you basically a complete information about the state today. Yeah, so this does not actually hold in general. If you have sufficiently informative transition model, you can say quite a lot about the weather today. Okay, that's not really true in practice. Usually these conditional probability tables are do not have this clear distinction, right? They have some fuzzy probability values here. But still, you can use them in modifying your beliefs in the distribution over the states. Okay, so that was this quiz. Using this update that we made here, basically, right? Going from yesterday to today and computing the new distribution, you may have actually say, okay, so let's move on one day. So now we have this distribution. Instead of 0.5, 0.5, we have 0.4 and 0.6. And you can basically repeat the computations and get the estimates for tomorrow and for the day after tomorrow and for the day after tomorrow. Okay. This is what is called a prediction. You want to estimate a future state or future distribution over the states. And in this case, this is quite very, very simple process. You just repeat this computation so many times as you need it. And yeah, so This is the current weather. Using the transitional model, you will get the future model. And then you will move one step ahead. You will move the current weather as the previous one, and you will compute again the new value for the distribution. So this is the known transition probability, and this is either known from some prior distribution where you set that the process starts, or it is a previous step of the forward simulation. Now imagine what would happen with this process of estimating the distribution to the future if you, for example, start with a different initial distribution. And let's look at two opposite cases. When you start with sunny weather for sure and no rain, basically, and with the opposite case that you have that there is for sure not sunny weather, there is for sure rain, right? If you apply this this recursive procedure, you will observe that these distributions actually converge to values 0.75 and 0.25 for our particular transition model. And it will converge also in the other case, in the opposite case, to the same values. And this is an example of what is called a stationary distribution of the Markov chain. And basically, it removes all the dependence on the initial state, and only the transition model determines what the final stationary distribution is. The stationary distribution is actually a very important concept in Markov models, and basically it is a limiting distribution for time going to infinity, okay? And for that case, it must actually hold that the distribution at infinity is equal to, let's say, the distribution at infinity plus 1, which is computed like this, right? This is just the mini-forward algorithm with the p infinity here. And if you think about it, then if the Markov chain is regular, which means that it fulfills some constraints or limitations, then it has a stationary distribution that can be computed explicitly directly from this transitional model. So this part defines a set of equations that can be, for our example, described like this. And if you put there the values from the transition model, then you can basically derive two equations that are not independent of each other, because one describes the same thing as the previous one. But if you solve it, then you will get basically the stationary distribution for our case. Okay, now I do have another question for you. We have talked about the stationarity assumption and about the stationary distribution. Stationary assumption means that all these transition probabilities are actually the same. The stationary distribution means basically this concept that it is at the limiting distribution of the mini-forward algorithm. And the question for you is, what is the relation of the stationary assumption and the stationary distribution? option A is that they are basically the same things, and the stationary assumption holds if and only if the Markov chain has a stationary distribution. Option B is that the two concepts are different, but stationarity assumptions guarantees the existence of the stationary distribution. Option C is that the concepts are different, but if the stationarity assumption does not hold and the transition probabilities do not converge, then the Markov chain cannot have a stationary distribution. And option D is that these two things are mostly unrelated, and the word stationary is used in two different contexts, let's say it like this. So what do you think? Which of the answers is most correct according to you? And maybe just answer this by your feeling rather than trying to deduce something from what you know. Okay, so thank you for your votes. Yeah, the distribution is quite spread. My intention with this quiz was to basically point to a very common misconception with students, that they really confuse the stationarity assumption with the stationary distribution. So very often when I asked it during the exam about stationarity assumption, they answer something about stationary distribution or vice versa. So this is just meant as a kind of reminder that these things are different. From my point of view, option C is the most correct one. They are definitely different concepts. They have some relation in the sense that if the stationarity assumption does not hold uh, and the transition probabilities do not converge in that non-stationary world, then the Markov chain cannot have a stationary distribution. Quite a good approach is to maybe think of these two things as option D, that they are mostly unrelated and that the word stationary is just used in two different contexts, basically. It is more profitable for you to think about it like this than to confuse these things one for another. Okay, and the last thing that I would like to talk about in the context of Markov models is actually something that is called Google PageRank. I don't know whether you have already read or heard about this, but it is an algorithm that Google used to use to order the results of their search engine. So the problem of finding relevant results for your query is relatively easy to solve, but the problem of presenting the results to the user is something quite different, and that is solved by Google PageRank. And you would like to present the most relevant or most important results as the first as the first option, basically, or first 5. And those less important maybe leave to second, third, 100th page of the results, right? And basically, the Google PageRank algorithm is an application of Markov chain, where you have some, let's say, a set of web pages which are somehow connected with hyperlinks. One can lead to another, etc. And the PageRank basically somehow estimates the importance of individual pages. And they do that using some kind of random surfer. That starts at a randomly chosen page. It selects one of the links in the page randomly, and it will follow it. So for example, to this page. Then it will select again one of the links randomly, and it will follow it. On this page, you don't have any outgoing link, so you start the process over, etc. And if you do that for a long time, then the number of visits at individual pages is basically proportional, let's say, to the importance of the page. At least that's how it is defined. And it can be shown that it is basically the stationary distribution of a Markov chain, where the transition models are basically modeled with the number of links between the pages. So the good pages are referenced more often, and they will then have the precedence in the final ordering at Google. Nowadays, the search engines use quite other factors to order the individual results, but the Google PageRank was a famous example, because when Google came with this ordering, it was really a breakthrough. And because of that, Google basically became the search engine, the one that provides best results. It was not because the other wouldn't provide the same results as Google, but Google was able to order them in much more profitable way for the user. Okay, so that was a brief introduction into Markov chains. So let's now move to hidden Markov models, which are much more interesting kind of model. Despite the Google PageRank is a very very successful application of pure Markov chains, basically, then they are actually not that useful in practice, because they assume that all the states variables are observable. Hidden Markov models, on the other hand, can basically describe the world as a pair of hidden variables and observable variables. So now we will talk about xt to be the hidden state variables and et to be the observable ones. Sometimes we will call them evidence variables or effects. This is basically the same distinction that we used in the first lecture when we talked about Bayesian framework for decision making. We used K for the hidden variables and X for the observations, but yeah, this is just a change in the notation. And very often, if you talk about hidden Markov models, this notation is used of X and E. That's why we adopted it here as well. In general, The probability distribution over possible current states and observations given the past states and observations can be described using this conditional probability distribution. We still assume the Markov property, meaning that the current state and current observations depend only on finite number of previous states, most probably only on the last state. And we also assume the stationarity, meaning that the statistical properties of the transitional model do not change in time. And we also add some other two assumptions. The first one is that the past observations have no effect on the current state and on current observation if you know the one but last state. Yeah, so basically this original conditional probability reduces to this one, right? That knowing this one previous state basically cuts out all the other dependencies that could have been there. Only this previous state matters in determining the current state and current observation. And we also use another assumption, which means that the current observation is independent of previous state if you know the current state. And this together basically gives us this kind of structure that we will use for our hidden Markov models, where these transitions are basically the transition model. They are described by this probability of xt given xt minus 1. And this is also here and also here and also here. And they are described by this emission probability, which is the probability of emission at time t given the state at time t. And these are these arrows pointing downwards. And altogether, this gives you a very simple factorization of this factor, basically to the transition model and to the emission model. So altogether, if you want to define a hidden Markov model, you need to state the initial distribution over the state x at time 0, so px0. You have to state the transitional model, which is basically the same thing as in the regular Markov chains. And what is added basically to hidden Markov models is this emission or sensor model, which describes what is the probability of individual observations given the current state. And all this together, if you want to describe the joint probability distribution over the sequence of hidden states from time 0 to t, and over the sequence of observations from time 1 to t, you can basically factorize it to this kind of model. So you have the initial state, the transitional model, and the sensor model. Yeah, and there are a number of independence assumptions. We talked about this already several times, so I will just skip this. Yeah. What are the possible applications of hidden Markov models? They were very often used for speech recognition, where the observations were actually the acoustic signals, the sound frequencies that you hear, and the hidden state was the phoneme, was the character that you try to pronounce, right? Or, for example, in machine translation. So the observations are words in the source language, and the hidden states X was basically the translations in the target language. Or handwriting recognition. You observe the pen movements and you basically try to estimate what characters these pen movements actually represent. In a time series analysis for biological signals like EKG or EEG, you observe the signals and you try to somehow estimate the hidden signal characteristics, meaning whether the signal is in normal state or some abnormal state, for example. Yeah, etc., etc. So there are numerous applications of hidden Markov models with different meaning of observations and hidden states for each application. We will use this example, this running example of weather umbrella domain to describe or introduce some methods for reasoning over hidden Markov models. And this weather umbrella domain is basically the situation that you are maybe a student which is locked by a supervisor in a computer lab or robotic lab, and this lab has no windows, so you have no chance to learn what is the weather outside today. Maybe you are logged there for several days and your only indication of the weather outside is whether your boss or your supervisor basically brings an umbrella with him or her each day. So you can somehow assume that if it is rainy outside or if the rain actually is going to happen, then your boss will bring the umbrella with him. And if it is sunny, then he or she will probably not bring the umbrella. So these are your observations, whether your boss brings brings his or her umbrella or not. And your hidden state is basically what you want to estimate, the weather outside. You cannot directly observe it. Okay. So this domain has basically this kind of structure. So the hidden state is the random variable R, which means whether it is raining or not. And the observations are the random variables U, which means whether the boss bring or did not bring his or her umbrella. So the whole domain is described by this transition model here. So how the rainy weather changes, that's given some historical observations or some experience, you can assume that this kind of model somehow exists. For example, if it was yesterday rainy, it will stay rainy today with probability of 70%. If it was rainy yesterday, it will change to sunny weather with probability of 30%, etc. But if it was, for example, sunny or not rainy yesterday, it will stay not rainy for today with quite large probability of 0.9. And this is the emission model that describes basically the behavior of your boss with the umbrella given the weather outside. So if the weather is rainy, he will highly probably take the umbrella with him. If it is rainy, well, yeah, with low probability, he will forget to bring his umbrella, maybe. And if it is not rainy, again, he will, with quite large probability, not bring his umbrella with him. But maybe he is more cautious and he says, okay, what if? So maybe there is 20% of cases that he will bring an umbrella even if there is not rain outside. Okay, so that's the meaning of these transitional and emission models. And these things together specify one particular case of hidden Markov model that describes this weather umbrella domain. And if we have this specification, now the question is what we can do with hidden Markov model. What kind of tasks we can perform with it. And this is an important thing, right? So try to understand what's going on here. The first task, and we will talk about this task today because we want to implement it today in code, is the filtering task. And filtering is this kind of thing. You have this sequence of hidden states, and you have these observations. And this is basically the sequence of particular observations from time 1 to time t. And based on these observations, you want to somehow model or estimate the probability of the hidden variable at time t given all these observations. Yeah, so you are after this quantity. You will learn that we solve this task by something called forward algorithm. It's not that hard, basically. But yeah, so this is the definition, right? The definition of the task. Given all the observation sequence, we want to estimate the last hidden state. That's filtering. Then there is the prediction task, which means that, yeah, if you have this hidden Markov model with the observations, you would like to basically predict some future or distribution of some future state. So given this observation sequence, this is the E1 to T, you would like to predict some future state. And you will see that it's basically a very simple thing that you will first apply filtering to estimate the current state. And then you will apply the mini forward algorithm that takes into account only the transition probabilities, and you will just advance to this state. So yeah, that's very simple. 2 parts, and both of them we will know at the point when we will optimize, implement it. Then there is this task of smoothing, and there is an important distinction between smoothing. It again is about the hidden Markov model and about some observation sequence that you have here. You have this observation sequence from E from 1 to P, or how it is denoted here. But your task is not to estimate this last distribution, which would be a filtering task. Your task is to estimate some distribution in the middle here. The probability of some past state given all the observation that you have. And it will be shown that it will be somehow split into 2 parts, that you will apply forward algorithm basically for this part. So you will estimate the probability distribution here, and then you will somehow incorporate the future observation to that state with a backward part, right? And we will solve it with the so-called forward-backward algorithm. But I'm not sure whether we will talk about it today. Hopefully, yes, but yeah, we will see. And then there are maybe 3 other tasks that you can try to solve using hidden Markov models. The 4th task is the so-called recognition or evaluation of a statistical model. And the task here is basically to compute the likelihood of the probabilistic model. Probability of observing the data given the hidden Markov model parameters. This will basically allow you to choose if you have more hidden Markov models describing the same application area with different parameters. It will allow you to choose which of them is the most likely one that generated the data that you observe. So you may have, for example, a hidden Markov model that generates various sounds, given, I don't know, some hidden states, and you may then, after observing or listening to the sound, you may decide which of the models basically produced it. So you may have different models for different words, so you can judge which word was the one that basically was used to produce the sound of the word. And we will see that the forward algorithm that is used for filtering, that was the first task, can be actually used also for this task. So no new algorithm here. Then there is a very important task of most likely explanation. And this basically means that based on the observed sequence of observations, you want to estimate the most probable sequence of hidden states. And this is solved using the Viterbi algorithm, which is a specific instance of dynamic programming. And this kind of algorithm is really important because it is used very widely in speech recognition, in reconstructing of bit strings transmitted over noisy channel or something like that. So very important algorithm to actually master. And then there is this 6th task, which is the hidden Markov model learning, which answers the question how you can estimate the parameters of the transition and the emission models from the observed data. So how you can learn the model from data. And this task is solved by the so-called Baum-Welch algorithm, which is a special instance of the EM algorithm that we will talk about next week. Okay, so let's move on to individual tasks and how they can be solved. First, we will talk about the filtering. Imagine what happens, right? So you have some initial distribution or initial belief over the states at time 0. And you know that something happens, right? The state advances to time 1, but you cannot directly observe it. What you will observe is something generated by the emission model as the first emission or observation. So you are interested in this part, in the distribution over the possible values of variable x1. And you would like to do the estimation based on the previous state and based on the current observation. And then something again happens, right? The time advances. There is the new state x2, which you can't observe. And you will observe a new value of the emission from the model. And again, you would like to be able to use the same thing such that you take the previous estimate of the states and the current emission, and you would like to update your belief over the current state. And this is something that describes how filters basically work, right? Well, if they filter some time series, then usually you compute the new estimate based on your last estimate and something that you learn, something that you observe. So we would like to basically create or find some kind of function which we now call temporarily as update, that would take the basically previous estimate of the states and the current observations, and it would compute the new estimate of the over the states. Okay. So it will be a kind of recursive algorithm that you will repeat over and over with new and new observations, and it will continuously update your belief in the state of the hidden variables. So the process will basically have two parts. In the first part, you will predict the current state at time t from the filtered estimate of the previous state, at the previous time, sorry. And once you will have this predicted state, you will update this prediction with the new evidence. So here you will basically employ the transition model, pxt given xt minus 1. And here you will employ the emission model, the probability of et given xt. And now how the updates are actually done. So now you have to be somehow passionate, or you will have to go through this alone at home, probably, where you can basically concentrate on the individual changes of these things here. But we want to compute this, right? So this is the same quantity. And we basically may split the observation sequence from time 1 to time t to observations from time 1 to t minus 1 and the last observation, right? That's what we can do, definitely. This is the explanation of what we did on that line. Now you can basically apply the bias rule to switch from the conditional distribution of x given e to a conditional distribution of e given x, right? So try to maybe first forget about the conditioning of this part, and you should see here some parts of quite known Bayesian theorem, right? So pxt is proportional to PET given xt times pxt. The alpha here is just the standardization or normalization constant, which is the probability of ET. But you don't have to compute it actually. So it is sufficient to write, okay, there is some constant, I will standardize it or normalize the distribution after the computation is ready. So I just crossed out these conditional parts to make it more clear that there is really a bias rule applied, right? But you cannot basically remove them. They are still present there. But if you now have this part, you can apply the Markov assumption that the observation at time t depends only on the current state and not on the previous states. So you can really get rid of this thing here to get this part. So we have found a first step in the filtering algorithm that you can compute this quantity by this thing here. And you can see that this is basically the emission model, right? Now there is a question how we can compute this. So it is a kind of one-step prediction, and we compute it using, again, some other computations, basically. Okay. So the quantity that we still need to somehow compute is this one, the probability of the distribution over the states of current time, given the previous observations. And now we can do some manipulations again. We can split, for example, the we can express this probability as the sum over the joint distribution of xt and all the previous states. That's something that we can do always. And then you can introduce basically conditioning on the previous state and modify this probability to this product. And once again, if you apply the Markov assumption, you can get rid of all the previous observations and you will find this result here. And basically, this is the transition model. And yeah, this is basically the filtered estimate from last step, right? You want to find ext given e from 1 to t. But here we have probability of xt minus 1 given the observation sequence from 1 to t minus 1. This is basically the same quantity. The difference is only one time step, right? We have basically found what we wanted. We wanted a method how we can update our estimate from the previous time step to get the current one. Yeah, yeah. The arrow here should be in the opposite direction. The time step is from right to left here. So altogether, the filtering algorithm is basically expressed using this this equation that the current estimate or new estimate is just a normalization using the sensor model, the transition model, and the previous estimate of the states. This is a quite nice equation, I would say, that allows you to filter sequentially as the observations arrive your belief in the state of hidden variables. We have basically split it or derived it in two different steps, and we will also implement it in the labs in two different steps. So We will basically use this this slide and these two equations in the labs today to actually implement the forward algorithm. So this is the update for one time step where you use the transition model, and this is the update for new evidence when you have your updated or predicted state and your current observation to get the final belief over the hidden states. Okay. So the whole forward algorithm, there may be some confusion. Let me explain it. Here are used this normal notation of probability of xt given e from 1 to t, right? To describe the estimate or belief distribution over the hidden states. On this slide, I just replaced this belief distribution over the hidden states by this bx, right? It is the current belief step over x, and it is actually defined as this probability. And on this slide, where I basically describe the forward algorithm, again, instead of this probability or instead of this bx, I use this ft. I will write it in a different way. Over xt. And all these three things mean basically the same thing. It's the distribution, probability distribution over hidden states. And now we call it a forward message that is basically passed forward through the hidden Markov model. I use these three notations not to trying to to somehow mess it up, but because it somehow emphasizes three different views on the forward algorithm, right? It is a probability. It is also a belief, your current belief over the state in time. And it is also a kind of message which is passed from one iteration to the other iteration in the forward algorithm. That's why we use basically three names for the same thing. So don't be surprised if you will find that they are the same. They really are the same. So the forward message is basically defined again as this probability that we are trying to model. It is computed as this that we already know. This is the forward message from time t minus 1, and you compute the forward message for time t using the transition and emission models. And you can implement it in a single function that should be called something like forward update or forward step or something like that. That takes the previous estimate and the current observation as the parameters, and it will produce something which can be turned into the new estimate. These are distributions, vectors of numbers. Okay, it's not a single number. So let's see the forward algorithm in action in case of the umbrella example or weather umbrella example. So this is the transition model, and this is the emission model that we already introduced a few slides ago. And let's look at day 0, right? So we are in a state here where we have the distribution of rainy and not rainy to be 0.5 to 0.5, blah, blah, blah. And that's our current belief, basically. We can't say much. right? We don't have any observation whether the boss brought an umbrella or not. It's simply the time where we still don't have any observation yet. To move to time 1, so you are in the situation when the distribution was 50-50, right? 0.5, 0.5. And you now observe that your boss brought an umbrella on day 1. Based on these two things, on this distribution 0.5, 0.5, and the information that your boss brought an umbrella, you want to update this pair of numbers to a new pair of numbers that would somehow describe your current belief, what is the weather outside. So how do you do that? You will first do a prediction. You will use the transition model here and your current belief over the state, or previous belief, pardon me, previous belief over the states to predict one step ahead and get the prediction of the weather for today. And this is basically done using this computation such that you will basically use the distribution over the possible states for one previous state. So that's 0.7, 0.3 times 0.5, which is the prior distribution here. And you will take the other times the other 0.5, and you will get your new estimate of 0.4 and 0.6. So if you had no information whether your boss brought an umbrella or not at day 1, your best guess would be that the plus rain value has the probability of 0.4 and minus rain would have the probability of 0.6. But now you learn that your boss bought an umbrella, and you can update by this evidence and renormalize the distribution. So how do you do that? Well, you will just say, okay, my boss brought an umbrella, which is basically this thing. I will use this pair of numbers here, and I will use my current belief of what the states are. I will multiply these vectors to get this pair, and after renormalizing such that the sum of them is equal to 1, I will get new estimate of the hidden states, of the probability of the hidden states. So we were in the situation where our distribution was 0.5, 0.5. Then we observed that our boss brought an umbrella, and based on these two informations, we basically updated our belief of the distribution over hidden states to 0.75, 0.25. Because bringing an umbrella is quite strongly correlated with the rain, we can somehow judge that the probability of rainy weather outside should be larger if we observe that the boss brought an umbrella. And you can do that for another day. So you have your current estimate or current belief over your states. And also you have, again, these two things in the transition model. So you will use same basically method to compute it. And you will use the updated probabilities of hidden states. You will get your new estimate. before you learn that your boss brought an umbrella on day 2. After you learn that, you can update again your current estimate with the evidence, and you can again use this use this current belief in the computation together with the distribution that corresponds to the real observation. No. Your current belief, you know that your boss brought an umbrella on day 2, so that's this column basically. You will use this column here, and you multiply by items, you renormalize, and you get your new estimate over the hidden states. So you can see that after observing your boss bringing an umbrella 2 times, 2 days after each other, you will get the updated distribution that tells you that on day 2, probably there is 84% or 85% chance of rainy weather outside. Okay. And I can see that the time has already passed, but I would still like to go through at least 2 other slides. So let me continue a few minutes. Now let's talk about the second task that you can do with hidden Markov models. That's the prediction. And as you can see, the prediction is basically defined as estimating the probability distribution at some future time if t denotes basically denotes the current state, given the observation sequence from time 1 to the current state. So it's something like this, right? You have the hidden states, you have some observations up to ET, and you would like to somehow predict to the future. Predict the distribution at time E plus K plus 1. And this is what is the prediction algorithm for, and it's really just the filtering that estimates the probability here, and then the prediction, the mini forward algorithm that estimates the future states without updating for evidence. So this is very easy to combine these 2 things together, and you will do that in the lab exercise today. And the last thing that I would like to talk about is the model evaluation, the computing of the likelihood of the model given the data. And I will just say this, that instead of the forward message that was used in the forward algorithm for computing the distribution over the probability over the hidden states, you can now pass through the forward algorithm the so-called likelihood message. Now the likelihood message is defined like this, and that's a difference. There is a slight difference from the forward message, which was defined like the conditional probability of xt given the whole sequence of observations. This is a joint probability. So that's the only difference between these 2 things. So you can basically compute this likelihood message and pass it through the forward algorithm the same way as you did for the forward message. And in the end, after you computed the likelihood message for the last time, for the last time window, you can basically zoom the vector, the message together, and this will give you the likelihood of the hidden Markov model that you are using with respect to the data, to the observations. And that's it. You are basically able to use this forward algorithm to evaluate how well 1, 2, 3, 4, any number of hidden Markov models fit to the observations that you have. And you can choose the one that fits the most. Then you have a kind of classification task, right? You choose one of the variables, one of the models, basically. Okay, and at this point, I would basically conclude today's lecture. We have covered Markov chains without those hidden parts, and we have started to talk about hidden Markov models, what they are, what probabilistic model they encode, and what things you can do with them. Those were those 6 tasks that we talk about. And we have gone through 3 of those tasks, which from which the filtering is the most important one. And we will basically implement filtering in today's lecture labs, right? So in a few hours, you will have basically implemented this kind of algorithm. And that's it. So thank you for your attention. We will talk about the rest of the hidden Markov model stuff next week. And yeah, see you in a few minutes in the labs.